At the heart of integrating renewables into the grid are inverter-based resources, or IBRs. In most cases, we need to deal with the variability of resources, but we also have the benefit of flexible control and many options for grid support delivered through these IBRs. The reality is that power electronics are ubiquitous in the energy transition. Regardless of how we generate or store our energy, from small solar systems in our houses to large-scale offshore wind turbines, all these systems connect to the grid through power electronics converters. These technologies enable the conversion and control of electrical power, ensuring that it can be efficiently and safely integrated into our existing power systems. Their role extends beyond mere conversion. They are pivotal in managing the grid stability and reliability in the face of increasing renewable penetration. Understanding where inverter-based resources connect in the power system is crucial. They link at both the transmission and distribution levels, each with unique implications. Identifying these connection points helps address specific integration challenges and leverage IBR benefits effectively. At the transmission level, we encounter distinct challenges: system strength, stability, protection coordination, black start capabilities. These issues require redefining system strength metrics, enhancing protection schemes, and ensuring that renewables can support the grid during and after disruptions. Addressing these challenges is critical for maintaining grid reliability and resilience in an increasingly renewable-dominated landscape. Similarly, the distribution level presents its set of challenges, including voltage regulation, power quality, and reverse power flows. Managing substantial voltage rise and ensuring harmonics, voltage sags, voltage swells, and flicker remain within acceptable limits are key. Moreover, coordinating protection in a grid with bidirectional flows underscores the need for innovative solutions to maintain stability and reliability. Before looking at some of the solutions of our ongoing challenges, we will discuss some key concepts fundamental to the operation of the power system. The heartbeat of the AC power system is its frequency. It corresponds to the number of cycles, typically of the sinusoidal voltage, that occur each second. It also serves as an indicator of the balance between generation and load at any given time. We want to keep our frequency relatively closely to its nominal value, because if we don't, typically bad things tend to happen to the power system. Another key concept is that of inertia. It is the kinetic energy that is stored in the rotating mass of electric machines, the synchronous generators that produce the bulk of power in our power systems. We can also see it as the resistance of the power system to changes in its frequency. So the higher the inertia, the easier it is to keep our system frequency within the frequency limits. When contingency events occur in the network, the stored kinetic energy in the generators serves to maintain the balance between generators and consumption. Excess generation will lead in an increase in the frequency, whereas excess consumption will decrease the frequency of the power system. The natural response due to the inertia of the generators is what we call an inertial response. This inertial response does not depend on the power output of the generators at any given time. At the short time interval following a grid disturbance and due to imbalance between generation and consumption, the frequency of the grid will change. The rate of this change of frequency can be calculated based on parameters that we know from our power system. These include Ke, which is the total kinetic energy of all generators in the system, and delta P, which is the difference between the mechanical input and the electrical output. The electrical output is the one that is changing because we have lost something in our system, whereas the mechanical power is staying constant. For a local example, we can look at a disturbance event that happened in October of 2018 here in Australia. We have a disconnection of an interconnector between New South Wales and Queensland, and because of this difference of generation and consumption at the two areas of the system, we can see the frequency in Queensland increasing, whereas the frequency in the remaining part of the network starts to decrease. A few seconds later, the interconnector between Victoria and South Australia also trips, and the excess generation in South Australia leads to an increase in the frequency, as we can see in the second part of this figure.